We went to the moon 6 times. 12 people walked on it. We did that with 1960s technology, slide rules, and computers less powerful than the phone in your pocket. So the question feels reasonable. Why, more than 50 years later, has no one walked on Mars? The answer is not political will. It is not funding. It is not a lack of imagination. It is physics. And physics, unlike budgets, does not negotiate. By the time we work through this, you will understand exactly what stands between us and the red planet. Not in vague terms. In the specific, unforgiving terms that every engineer working on this problem has to reckon with every single day. Before the obstacles make sense, the distances have to make sense. And most people's intuition here is significantly off. When we talk about astronauts going to space, we are almost always talking about low Earth orbit, the region a few hundred kilometers above the surface where the International Space Station lives. The station sits roughly 400 kilometers up. To put that in terms you can feel, if you drove from the center of Los Angeles straight upward at highway speed, you would reach the station in about 3.5 hours. It is close. The moon is not close. The moon orbits Earth at an average distance of 384,000 kilometers, roughly 1,000 times higher than the station. Apollo got there in 3 days. That already felt like a different category of mission. It was. Mars is in a different category again. At its closest approach, a favorable alignment that occurs roughly every 26 months, Mars sits about 54 million kilometers from Earth. That is 140 times the distance to the moon. At its farthest, the separation grows to over 400 million kilometers. There is no single distance to Mars. There is a range, and your launch window determines where in that range you start from. That number alone begins to explain everything that follows. The most direct way to see why Mars is hard is to line up 3 missions side by side and watch what the numbers do. In 1962, John Glenn's Mercury 6 mission carried 1 astronaut to an altitude of about 200 kilometers in a capsule weighing 1.2 tons, launched on a rocket weighing 120 tons. The mission lasted 5 hours. 1 person, 1 day, a few hundred kilometers up. Apollo 17, the last crewed mission to the moon, carried 3 astronauts in a combined spacecraft weighing about 50 tons, launched on a Saturn V rocket weighing 3,000 tons. The mission lasted 12.5 days. 2 astronauts walked on the moon for just over 3 days while a third waited in lunar orbit. From 1 person for 5 hours to 3 people for 12 days, the rocket mass grew by a factor of 25. Now consider a proposed crewed Mars mission. 6 astronauts. 174 days to get there. 539 days on the surface, waiting for the orbital alignment that makes the return trip fuel efficient. 201 days to get back. A total of just over 900 days, roughly 2.5 years, from the moment the engines ignite to the moment the crew steps back onto Earth. 6 crew members instead of 3. A journey 73 times longer than Apollo. The supplies required scale accordingly. Estimates put the consumables alone: food, water, air, medical equipment, replacement parts, at roughly 150 times what the Apollo missions needed. Not because the crew is larger, mostly because the duration is almost incomprehensible by comparison. That mass has to travel with the crew, and mass in spaceflight costs propellant. And propellant is also mass. This is the problem that defines everything else. To reach Mars, a spacecraft has to leave Earth's orbit, transfer to a heliocentric orbit, meaning an orbit around the Sun rather than around Earth, and arrive at Mars moving slowly enough for the planet's gravity to capture it. Then, after the surface stay, it has to launch off Mars, navigate back across the solar system, and decelerate into Earth orbit. Each of those maneuvers requires fuel. Each kilogram of fuel you need requires more fuel to carry it there, which requires more fuel to carry that fuel, which requires more fuel to carry the fuel for the fuel. The mathematics compound ruthlessly. Current estimates for a round-trip crewed Mars mission put the propellant requirement somewhere between 850 and 1,250 tons. For reference, the International Space Station, the largest structure humanity has ever assembled in orbit, weighs about 420 tons. The fuel alone for a Mars mission would outweigh the station by a factor of 2 to 3. No single rocket currently flying can deliver that to orbit in one launch. Starship, when fully operational, aims to carry up to 200 tons to low Earth orbit, a genuine leap over anything that came before it. A Mars mission would still require multiple launches, multiple orbital rendezvous, and the assembly of the complete mission architecture in space before the crew departs. This is not a conceptual obstacle. It is a sequencing and logistics problem of real complexity, and it has not yet been demonstrated at anything approaching operational scale. Then there is the radiation problem, and it is worth being direct about it rather than glossing over it. On Earth, the planet's magnetic field deflects most of the high-energy particles streaming in from the Sun and from deep space. In low Earth orbit, the station benefits from partial protection within that field. The Moon missions lasted less than 2 weeks, short enough that radiation exposure, while elevated, was manageable. A Mars transit lasts 7 to 9 months each way, entirely outside Earth's protective field, in deep interplanetary space where there is no shielding except what the spacecraft provides. Current estimates suggest a full Mars mission would expose the crew to a total radiation dose, approaching the career lifetime limit set for NASA astronauts. And that limit exists specifically because exceeding it meaningfully raises the lifetime risk of cancer. Shielding helps. More shielding means more mass. More mass means more propellant. The cycle compounds again. The surface of Mars offers partial protection from cosmic radiation. The planet itself blocks roughly half the sky. But the thin atmosphere, about 1% of Earth's, stops very little of what comes from above. Astronauts on Mars would spend the majority of their time in pressurized structures. Extended surface operations would require suits with enhanced shielding, adding weight and constraining mobility. This is a solvable engineering problem. It has not yet been solved. Alongside the physical challenges, the biological ones run parallel, and they are less discussed but equally real. After 6 months in microgravity, the human body has changed in ways that matter operationally. Bone density decreases. Muscles weaken. The cardiovascular system adapts to conditions that do not exist on a planetary surface. Astronauts returning from long-duration missions on the International Space Station routinely require weeks of rehabilitation before they can walk normally. Now consider that the crew arriving at Mars would face all of this immediately upon landing, on a world with 1/3 of Earth's gravity, in an environment that requires suit operations and physical work from nearly the first day. We do not yet know with confidence that a crew could perform meaningful surface operations after a 7 to 9 month transit without an extended recovery period. That recovery period would have to be built into the mission timeline. And the mission timeline is already the tightest constraint. The psychological dimension adds its own weight. 2.5 years is a long time to be confined to a spacecraft smaller than a typical apartment, with a small fixed group of people, under constant low-level stress, with no possibility of emergency evacuation, and no real-time communication with anyone outside the vehicle. Even at the speed of light, a radio signal takes between 3 and 22 minutes to travel between Earth and Mars, depending on orbital position. A question asked from the surface gets an answer somewhere between 6 minutes and 44 minutes later, in the best and worst cases. Mission control cannot intervene in a crisis in real time. The crew is on their own, in a way that no human crew has ever been. None of this is cataloged here to suggest the mission is impossible. It is cataloged here because understanding the obstacles is the precondition for solving them. Here is the honest state of things. The trajectory exists. The orbital mechanics are understood. The launch vehicles are improving. The biology is partially understood, and the gaps are being actively studied. The propulsion technology is the most significant open question. Chemical rockets can get us there, but at a cost in mass and time that makes the mission extraordinarily complex. Advanced propulsion concepts, including nuclear thermal systems that could cut transit times roughly in half, exist in prototype form but have not been qualified for crewed spaceflight. The gap between where we are and a crewed Mars landing is not theoretical. It is a specific list of engineering and biological problems, most of which have credible paths to solution, and none of which have yet been demonstrated at flight-ready maturity. A century ago, crossing the Atlantic by air was considered a stunt. 50 years ago, walking on the moon was considered the limit of human ambition. The metric for what counts as reachable has moved before. It moves because people decided the problem was worth solving and committed the resources that decision requires. Carl Sagan spent the latter part of his life making the case that Mars was not a destination, but a responsibility. That a species capable of extinction by any number of causes had a fundamental interest in becoming multiplanetary, however long that took. He was not predicting a timeline. He was describing a direction. The distance to Mars is real. The radiation is real. The propellant math is real. The biological unknowns are real. And so is the trajectory. The slow accumulation of capability, mission by mission, that brought us from John Glenn's 5-hour orbit to 12 people on the moon, to robots currently drilling rock samples on the Martian surface and loading them into a cache for a future return mission. That cache is sitting on Mars right now, waiting. We are closer to this than the difficulties suggest, and further than the optimism implies. That is the honest position, and it is, in its own way, exactly where you want to be on a problem worth solving.